Hello and welcome to everyone attending. We have prepared this presentation to refresh the audience on some basic information that are vital to the use of FTIR but are often easily missed. We'll provide a general overview of the capabilities of FTIR, FTIR accessories, and good practices that are essential for producing quality data. In addition, tips and tricks and some key precautions are also discussed. We'll go over a few key topics today, and they are organized as shown in this overview slide. First, ways of sample preparation and measurements for different kinds of samples will be discussed with mentions and/or details of various kinds of accessories. Then, we'll briefly describe the use of ATR accessory along with its advantages, disadvantages, and things to remember. Next, the effects on the FTIR instrumentation and FTIR spectra caused by moisture and carbon dioxide in the air and ways to mitigate them will be examined. After that, we'll cover some key precautions when using the library match to identify unknowns. As you know, library search is one of the most used features by FTIR users, but can cause problems if precautions are not taken. Finally, a brief overview of FTIR microscopy will be provided with some interesting application examples of microanalysis using FTIR microscope. First, let's go over measurement techniques we are all familiar with and have been around for a long time, namely KBR pellet method and liquid cells. With the KBR method, the solid or powder sample is ground, mixed with KBR and pellet prepared for transmission measurement. This method can be used for both qualitative and quantitative studies. Similarly, for liquids, the sample is simply sandwiched between two pellets for measurements for qualitative measurements. For quantitative measurements of liquids, liquid cells can be used. Pictures on the right shows examples of the accessories and samples. For solid analysis, as well as for liquid analysis. These days, there are a lot of accessories for FTIR available. I've covered some of the most commonly used ones in this slide. Attenuated total reflectance, or simply referred to as ATR in short, is probably the most used FTIR accessory. It allows the user to simply drop the sample onto it and take the measurement. No more preparing or grinding the sample to make pellets. It will be discussed in more details in the upcoming slides. In addition to ATR, there are diffuse reflectance measurement accessories for quantitative analysis of powder and solid samples. Similarly, specular reflectance accessories are used for solid samples with shinier and smoother surface. For liquids, ATR can be used, as well as more newer transmission accessory with easy loading and cleaning capability that are available. FTIR are also used for measurements of gases, and there are a wide range of gas cells available, including some with path length as long as 30 meters. Finally, FTIR microscopes are popular for analyzing very small samples. They can be used in research as well as forensics, contaminant analysis, and general QA/QC in different kinds of fields. In the next few slides, we'll put focus on ATR. As many of you know, it is fair to say that ATR is the most commonly used FTIR accessory. In order to take a measurement, simply drop the sample onto the ATR crystal, press it with the provided anvil or clamp to ensure proper contact between the sample and crystal, and take the measurement. ATR accessory is simply placed on the sample compartment of FTIR spectrophotometers. As shown in the schematic on the right, inside an ATR, a mirror diverts the beam onto the crystal, where it is totally and internally reflected. Evanescence wave is generated at the point of contact between the sample and crystal, which penetrates about 2 to 5 microns into the sample. The absorption of this wave by sample results in attenuation of the IR beam inside the crystal, and IR absorbance measurement is obtained. In addition to the single bounce ATR shown in the schematics, multi-bounce ATR are also available, and they are used for certain specific applications. The contact between the crystal and sample is extremely vital, and this fact cannot be stressed enough. This is especially important for solid samples where using pressure clamp to properly clamp the sample is extremely important. For liquid samples, however, this is not a concern as long as the sample is dropped on the crystal. If the liquid is volatile, measures need to be taken to prevent or reduce evaporation during measurements. The right-hand side top picture is an example of ATR. Notice the pressure clamp on the top for pressing the sample. The bottom picture is the same ATR placed in the sample compartment of an FTIR spectrophotometer. ATR does have a set of advantages and disadvantages. As described earlier, one of its biggest advantages is that it is very easy to use and requires no sample prep. This makes the measurements very quick. Since the samples do not need to be grinded or cut, the technique is also non-destructive. Also, since the evanescent waves only penetrate about 5 microns into the sample, ATR is an excellent surface measurement technique for coating and for samples that are very thin. On the other hand, ATR measurement suffers from low signal-to-noise ratio. If you have a sample that is not known to absorb infrared very much, or if the absorbance is low in certain regions, ATR spectrum will show a lot of noise. Next, being surface analysis technique is also a disadvantage because there is a chance of erroneous measurement where there is a coating or contaminant on the surface of the sample that needs to be measured. Finally, since the intensity of spectrum changed based on the sample crystal contact, it is not recommended for quantitative analysis, mainly for solids, because of the pressure and sample surface variation between measurements. There are several precautions that need to be taken when measuring with ATR and analyzing spectra obtained from ATR. Here, I'll briefly go over the effect of use of different types of crystals. First and very important is that the crystals should have a high index of refraction than the sample. Luckily, majority of organic samples have refractive indices in the area of 1.5. Refractive indices of standard ATR crystals span from 2.4 to 4.0, which in most cases provides sufficient sample to crystal differentiation. However, the users must be mindful of peak shift when comparing ATR spectra of same sample measured using different crystals. For example, the top spectrum on the right in the slide is a spectrum of polyethylene terephthalate on zinc selenide crystal, which has refractive index value of 2.4, and the bottom spectrum is the same sample on germanium crystal, which has refractive index value of 4. Notice the peak shift, especially for the peaks that highly absorb. The peaks where this is significant are highlighted with large font size on each of the spectrum for your convenience. In summaries, there are 2 takeaways from this slide. The first one, the crystals should have higher index of refraction than the sample. Second, difference in refractive index ratios because of the type of crystal used will cause spectral differences. In this slide, we'll go over other key considerations when using the ATR. Again, just to go over it one last time, the crystal contact is extremely important. For example, if a hard plastic block needs to be measured, but it is not completely flat, it will have to be flattened for measurement. Or tiny particles can be scraped out for measurement. As described earlier, quantitative measurement for solids and powders is not recommended because of variations between pressure and contact between measurements. Another consideration, mainly when using the zinc selenide crystal, is that it is soft crystal and is susceptible to damage even with regular use. Although this is usually the most cost-effective crystal option, its use should be avoided, mainly when constant measurement need to be taken or when FTIR is used by multiple people throughout the day. Diamond crystal, on the other hand, should be used as much as possible, and it is good for almost all samples. Although it is the most expensive option when upfront cost is considered, its durability usually makes it the most cost-effective option in the long term. Now, on to our next topic, we will focus on the effect of moisture on FTIR optical components. As most of you know, even the normal amount of moisture in the air will cause damages to hygroscopic components in the interferometer of FTIR, mainly the beam splitter and windows. Therefore, the user should regularly check if the desiccant, often silica gel packets, are in good dry condition and replace as necessary. In addition to these desiccant materials, Shimadzu FTIR spectrophotometers actually have an electronic dehumidifier system that constantly removes moisture from the interferometer. The system is always on as long as the power is connected and the instrument need not be operating. The schematic of the system is shown on the right, and this mechanism ensures that the instrument and its component last longer. In addition to the moisture causing damage to the optical component, both water vapor and carbon dioxide in the air absorb infrared and will almost always show up as noise in the spectrum. The graph on the right shows the reason where their spectral profiles show up. One important thing to remember is not to get too close to the sample while loading or preparing to load them to avoid breathing into them. As we know, our breath is full of water vapor and carbon dioxide, so doing so will directly result into bad or erroneous data. While water vapor and carbon dioxide affect all samples, they are a huge concern for gas analysis, and even a little bit can affect the data greatly. Good news is the effect of water vapor and carbon dioxide can be reduced, even eliminated. Most modern FTIR spectrophotometers allow purging with dry air. This will ensure that the internal part of spectrophotometer is completely free from water vapor and carbon dioxide. Again, for obvious reasons, refrain from breathing too close to the sample and sample compartment. Another way to reduce the effects due to moisture in the air is to make sure that the FTIR spectrophotometer is not directly under the AC vent. Similarly, avoid placing the instrument in an enclosed space like the fume hood. Finally, regularly check the desiccant, and using FTIR systems that come with electronic dehumidifier system in addition to the desiccant will help greatly too. In addition to these precautions, most modern FTIR software offer post-processing spectral corrections features to reduce the effect due to moisture and carbon dioxide. Now switching gear to move to our next section, we'll discuss about one of the most used features in FTIR software, the library search. It is safe to say that anybody who has used FTIR in the modern days have used this feature to identify their unknown materials or to check their samples against a known standard. FTIR libraries are extremely helpful. With the availability of wide range and varieties of libraries and advanced software, the ability to identify materials has improved significantly over the past several years. Commercial FTIR libraries are widely available, covering various fields like polymers, plastics, chemicals, forensics, food, agriculture, and many more. However, there are some important factors to consider when using them. One of the first and most important thing to remember is that FTIR libraries cannot and do not have everything. The software will search from what's in the library, and a spectrum for your unknown sample is not in the library. The match in the library will not be so great. Therefore, making custom libraries will often help, mainly if your sample is a rather unique substance or new material. Also, making a custom libraries can help users compare samples from different batches or against their perfect sample. For the same reasons described in the previous slide, it is very uncommon to get 100% match against a spectrum in the library, but it is okay. Remember, commercial libraries are created under ideal conditions and parameters, and oftentimes go through post-processing to clean them up. Therefore, it is wise to use library match as a good reference point. After that, checking for functional group peaks and other spectral characteristics are helpful for accurate identification. Post-processing, such as baseline correction and normalization, can help with this process too. Finally, it is important to keep measurement parameters consistent between measurements if spectra are to be compared. Similarly, search parameters should be kept consistent too. Changing algorithms in the software will vary results greatly, so it is important to understand how the search is affected with the change. Also, FTIR software allows for ability to select or deselect libraries and post-processing such as baseline correction for library search. It is important that these features are well understood and kept consistent between comparisons. Now that we've covered some of the key precautions for FTIR in the last few minutes of the presentation, I'd like to briefly introduce the technique of microanalysis using FTIR microscope. So, when does one need an FTIR microscope? A simple answer to this is when samples are micrometers apart, need to be distinguished, or very small sample need to be analyzed. These samples are impossible to analyze properly in the FTIR spectral photometer by itself, thus the need for microscope. FTIR microscopes can be used for a variety of applications such as contaminant analysis in pharmaceutical products or food, analyzing microplastics, optical components, identifying cause of defects in manufacturing, and many more. It is widely used in the field of forensics for evidence analysis and identification, and in the field of material science to understand defects and degradation. Next, we'll go over some of the applications of microanalysis using FTIR microscope. As many of you know, microplastics in ocean is becoming a huge problem. FTIR microscopes have proven to be a great tool for identifying microplastics in the water samples. In this slide, the left picture is a camera image of plastic samples obtained from a water body. To our naked eye, the plastics there all appear colorless and similar. However, FTIR microscopes can identify, quantify, and map them. The images on the right are the false color images of the same samples showing the distribution of three different kinds of plastics: polyethylene terephthalate, polypropylene, and polyethylene. On this next example, defect in micro SD card was analyzed. The lower zoomed in picture shows stains on the metal part that were causing issues for proper operation of the micro SD card. The top spectrum on the right is the spectrum from the stain. The two below it are library spectrum matches for fluorinated lubricants. Turns out the fluorinated lubricants are used as glue during the manufacturing process, and some of them got into the metal connection part of the micro SD card, causing it to malfunction. So, with the help of FTIR microscope, the problem was quickly identified. With this, we've reached the end of our presentation. I thank you for your time and attention and hope that the presentation was helpful.
Excellence in Science, Shimadzu.